The Simpson meter is not as esteemed as it once was. The digital meter now rules. If you are a modern electron chaser, chances are you have at least one digital multimeter and no analog meters. And for good reason. Most inexpensive digital meters are far more accurate and have far more functions. But I like these. They look good, they feel sturdy, they have history, and they are accurate for many of my needs. And I like how it goes like this. One thing that does often bite me while using these is the low input impedance. I'll be poking around a circuit and will not only be reading values that don't make sense, I'll be affecting the output of the circuit simply by taking a measurement. That's what this video is about. It's about me converting an old Simpson 260 meter into an abomination, into a high input impedance volt ohm milliampere meter. Here's a demonstration of the effect that the low input impedance of the meter has on your measurements. Down here I have two resistors set up as a voltage divider. They are both 20k ohm resistors. So the voltage between the two resistors will be half of the voltage that's put across them. Using the fluke meter up on the top right of the screen, I can show that the voltage across these two resistors is 1 volt. Seeing that this is a voltage divider, we would expect that if we measure right here in the middle, we would get half a volt. And there it is. Now let's use the Simpson meter to take the exact same measurement. First, I'll measure across the two resistors. You see I'm on the 1 volt scale, so at full scale we're measuring 1 volt. But now when I use the Simpson meter to measure the voltage divider, you would hope that the voltage would measure right here, or exactly half a volt. Let's see what happens. Instead of measuring a half a volt, I'm measuring a third of a volt. So why does the fluke meter provide the answer you expect or maybe want, and the Simpson meter don't? In short, the fluke meter has an input impedance of 10 mega ohms, and the Simpson meter has an input impedance of 20,000 ohms per volt. Hooking the fluke meter into the circuit looks like this. You're essentially placing a 10 mega ohm resistor across that output 20k ohm resistor. 20 kilo ohms in parallel with 10 mega ohms, which is approximately 20k ohms, meaning the measured output voltage is still half a volt. Now, what happens when we measure the circuit with the Simpson meter? Well, because we're on the 1 volt range, that's essentially like putting a 20k ohm resistor in parallel with that lower resistor. So, we have 10k over 10k plus 20k, which is equal to a third of a volt. Which is why we measure on the Simpson meter a third of a volt. This is the Simpson meter operator's manual. It's how an operator manual should be written. Nice font. It's nice and orange. It's only $1, which I spent $12.50 for. Shows you the devices that you should own. Has some nice pictures of the meter that you just bought. And in the back, it has this circuit. This is the part of the Simpson meter responsible for deflecting the needle. It's calibrated so this part of the meter measures voltages from 0 to 250 millivolts at this point right here. But the problem is, it measures a voltage from 0 to 250 millivolts, but has an input impedance of 5,000 ohms. That's the part of the meter that we want to change. So here's what I'm doing. I'm going to replace this old input stage with this new input stage. An op-amp will have very high impedance. The impedance of the op-amp is so high that I can set the impedance of this stage by this resistor. The op-amp is placed in this configuration to drive the needle from 0 to full scale when an input voltage at this point goes from 0 to 250 millivolts. The same range of voltages over here, but now I can make the input impedance what I want using this resistor. This pot is used to make the meter read full scale when I put 250 millivolts here at the input. To make the Simpson meter work at various ranges, I simply have to put another resistor at the front of this stage that will divide the voltage down from, say, 10 volts down to 250 millivolts using that high input resistance. This is the new high input impedance circuit that I will be putting into the Simpson meter. I'm repurposing the rotary switch from the original Simpson meter, these guys right here. I'm using this same rail in the rotary switch, and I'm hijacking the AC part of the switch and moving it over here. I flipped it around and put it right here. Those two rails allow me to switch in the various voltage ranges. 250 volts, 50 volts, 10 volts, 25 volts. You'll notice that I don't have a 500 volt range, and that's because the Simpson meter does something kind of funny with that in the rotary switch, and I don't need to be messing around with 500 volts anyway. I've also added the capability of using the current ranges. To include current ranges, I hijacked this part of the rotary switch and put it over here. So to measure various currents, I have 500 milliamps, 100 milliamps, 10 milliamps, and 1 milliamp. Down here, I hijacked part of the mode selection switch. Using this mode selection switch, I can select in different ranges that cause the needle to deflect from 0 to full scale. With this configuration, I'll have all the functionality that I want out of my high input impedance Simpson meter. Welcome to a new episode of ASMR Engineering. On today's episode, we're going to modify this Simpson 260 Series 6 meter to have a high input impedance at the terminals. This is the Simpson 260 Series 6 meter. I don't feel too bad about modifying this circuit because of all the modifications that have happened over the years. These are not original Simpson resistor parts. Fuse is missing here, second fuse missing down here. Somebody added new potentiometers. The goal will be to replace this circuit board right here and only keep the switches so that I can use the same switching to switch between the various voltages. I want to be able to use all the current meters inputs and all the voltage inputs. Okay, there we go. I hope this works. I didn't realize how attached I was to this meter. Came out pretty easy. This guy came out a little bit more chunky. Now I have my switches, and I'll make a drawings in KiCad that will fit to these holes so that I can replace this board. And I have this board now, so I'll be able to figure out exact locations where these holes go. Okay, let's go draw this up. So this is the circuit laid out. But over here, the different sections, I have my op amp section. Up here is my negative voltage supply. Made a footprint for these switches. Next step, take this, put it onto a copper board, and etch it. I do etching out in the shop because it gets a little chemically. My recipe is about 2 parts hydrogen peroxide and 1 part muriatic acid. And let sit. I actually don't know how long it takes to etch. Maybe 10-15 minutes. Well, there's your answer. It took about that long to etch the board. You'll notice that I put a giant ground plane on the front of the board. The only reason I did that was to minimize the time it took to etch the board. And for God's sakes, don't drink that. It's toxic. Not too shabby. Well, a little shabby. One problem right here is I forgot that these guys were on the board, so I didn't account for those. One of those guys goes right through my traces. See that? The other problem I had was there's a little bit of pitting. I don't know if you can see that. This kind of grain that you see right here. Anyway, next step, placing the components. You want to see my pick and place machine? I haven't mentioned it yet, but you might be interested in knowing which op amp I chose as the input. I need an op amp with large input impedance. The answer is I made my own. Part of the fun for me in this project was making all the electronics out of discrete components, no ICs. So this is a little op amp design used for the input of the circuit. What you see up here is really just this right here. It's the op amp and the ammeter. I chose to use MOSFETs as the input to the differential stage. That gives me my high impedance. And you might ask, how good is it? Well, it's not. Probably the best I get out of this is a gain in the thousands to tens of thousands. depending on whether or not I'm breathing. You may have noticed in my design for the operational amplifier that I need a negative voltage supply. For my negative voltage supply, I made my own. Sticking with the idea of only using discrete components, this negative voltage supply only uses a handful of BJTs that I found on the floor, some resistors, some caps, and a couple of diodes, doing the diode and capacitor thing down here at the bottom to provide a negative voltage supply. This is a good point to show off the circuit because this will literally be the prettiest this will be. After this point, I will have found 2 to 12 different errors that will make me have to rip into that board. That's the high input impedance. So the input comes through a couple of resistors straight into this guy right there. Because I'm making this out of discrete components, these two guys aren't completely matched and I need a little trim resistor to help me out there. I can control the current through that differential amplifier using that potentiometer. There's a current mirror generated by some resistors down here, and then the output stage comes up over here. This section right here is overcurrent protection. So if I go much above 50 microamps or below it, I can pin the current. I've also got a little bit more protection over here with some diodes, and for the current stage, I have this fusion line that will blow if it goes over 500 milliamps. My op amp sucks, so I need a negative voltage supply. This little negative voltage supply uses a oscillator right here. I buffer it and then I go through a couple of diodes to get a negative voltage. I'm using the potentiometer, decided to use that to zero out the voltage. It was used to zero out the resistance, but I'm not using resistance on this thing. You see that on things like vacuum tube voltmeters because the input isn't temperature stable. In fact, if I touch any one of these transistors up here, I can get little ammeter to drift. So I use this to pull it back into place once everything's up at a temperature. Right here, these trim pots to calibrate the 3 modes. I have it. This will make the input so that it's 25 millivolts input. This will make it so that's 250 millivolts input, and this one will make it 2.5 volts input. This is the input to the voltage stage, and it's just a few resistors that divide down the voltage to the 2.5 volt input. When I want to look at current, I have this stage down here. So far, I'm pretty happy with it. A little bit of an improvement over the old Simpson meter board. What do you think, Mr. Simpson? And for the reveal. There were far fewer errors than I thought there would be. I did have to rework a little of my protection circuitry because it was introducing nonlinearities. and I've decided not to use the 25 millivolt range of my mode select. But I like this. Let me show you how to use it. First, you turn it on and select between a 2.5 volt input or a 250 millivolt input, depending on what you want to measure. The 2.5 input is what I'll use most of the time because it is the mode used to select in voltage ranges from 2.5 volts to 250 volts. Say I want to measure something in the 0 to 10 volt range. I first switch to that range. I then zero out the input by shorting my leads and adjusting for 0 volts. This is the thing I was saying I needed to do earlier because of the homemade op amp I made. It's a problem with temperature stability. It's the same thing you have to do on a vacuum tube voltmeter. I can then use the meter as you'd expect. Here's 0 volts, 1 volt, 2 volt, all the way up to 10 volts. But now here's where the real magic happens. Remember earlier, maybe too long ago because this video is getting really long, where I measured a voltage divider made up of two 20k ohm resistors and the output voltage was 1/3 of a volt instead of 1/2 of a volt? Well, check this out. I'll repeat the measurement. First, I have the meter set up to measure a 1 volt range. I zeroed out the voltage by doing that thing, and here's the voltage across those two resistors. 1 volt. Now watch this. Yes! Woo! There are a couple downsides to the meter. One, the lowest voltage input setting, the 25 millivolt range, is too sensitive, which has to do with the large value potentiometer that comes with the meter and my not so stable op amp. Unfortunately, I was hoping to use the 25 millivolt input for my current meter stage. I can still use the current meter, but I can't use the 1 milliamp range or the 50 microamp range. It also means that my current input stage isn't any better than a non-violated Simpson 260 meter, so I'll just use one of my other meters when I want to measure current. Another issue with the meter is that it draws some current. Because of my garbage op amp and voltage supply, the thing swallows about 35 milliamps of current. So I placed two 9-volt batteries in the thing and ordered some more. It's really not too bad. I can get a few days of continuous 24-hour usage out of it. But I did make provisions for powering the meter externally, which doubles as a mechanism for testing the batteries. Also, this is one of the reasons why you wouldn't want to make one of these. One of the great things about these unmodified Simpson meters is that they use no power at all to measure both voltage and current. For a regular 260, the batteries are only used for measuring resistance, and you never draw much current. The batteries in the original Simpson meter were soldered in there for cripe's sakes. All things considered, I really like this. In the end, the input resistance ranges between 5 mega ohms and 20 mega ohms depending on the range select. That's more than enough for a good portion of my projects. And I'm sorry, that was a really long first video. Thanks for watching if you made it this far. Okay, well, see you later.